The purpose of this video is to discuss the question of how signals move up and down within the recursive hierarchy of the triangular neighborhood networks. But before we can do that, we have to understand why a particular edge in the middle of a ground state system, why a particular edge decides to move. The particular edge shown in purple is a member of two triangular neighborhoods. Rotation of the edge can occur by going either this way or this way. This is the logical diagram for edge rotation. This diagram introduces for the first time my sense of how the signals must be arranged so as to trigger the edge rotation. There has to be one signal going in this direction or one signal going in this direction. The signals one could think of as pulling the edge around. So in the beginning, all of the nodes in the two triangles are 6-edge nodes. As the rotation begins, we come to an intermediate state where these two 6-edge nodes become 5-edge nodes, and there are two transient 3-edge nodes. As the rotation finishes, then we have these two 6s become 7s, and then we have two 5s. Of course, the rotation could go in the opposite direction, in which case we'd have this logical diagram, and the signals would point in the opposite directions here. This is the starting state, this is the intermediate state, this is the final state. So in this case, there are two alternate ways of causing edge rotation and two alternate patterns of signals for causing the rotation. It's the causing the rotation that the signals do now. Of course, at the next level, lower level of structure, these edges would be pipes and these signals would be torus. So that's the recursive aspect of the triangular neighborhood network system. Now the edge rotation has been made, and you'll notice, as we saw before, that quite a bit of distortion has been introduced into the ground state. So this is the rotated state, now colored so that the 7-edge nodes are in pink and the 5-edge nodes are in light blue. I've changed the connector color from orange to purple because that gives better color distinction. Now what we'll do is we'll take this edge here and rotate it, and that will cause this defect to move in this direction. Now this defect here has moved by edge rotation to this position here. Once again, you notice the distortion in the ground state as these two defects move apart from each other. This is the logical diagram for the motion of the defect away from its creation. This is the 5-7 defect here. As before, there are two ways of rotating the edge. We can rotate this way or this way. I've chosen to go this way. This is the intermediate state, and this is the final state. So what we see is that the defect is moved from here to here, which in this terminal state is from here to here. What we've seen in this section is the pattern of signals that could be used to cause edge rotation. In this instance, it was to move the defect. Earlier, it was to create the defect from using an isolated edge as the place where the edge rotation occurs. We'll see later in this video how signals are arranged to cause the signal to move up or down in the hierarchy of the triangular neighborhood networks. One of the most important aspects of recursion in the triangular neighborhood networks is that signals can move from one level to the next. I've used this particular construct in my rapid prototyping tool to show the collision of three defects. As before, the 7-edge nodes are in pink and the 5-edge nodes are in light blue, and the connector is in purple. Now we have three defects. One defect is moving in this channel, one defect is moving in this channel, and one defect is moving in this channel. I'll move from state to state by doing edge rotations. One edge rotation here, one edge rotation here, one edge rotation here. The three edge rotations of the three defects have been made, and now the three defects are in contact with each other quite intimately. So this is the very center of their activity. The next rotations that will be made will be these three edges here, and this will bring the defects even closer together. The three defects have now merged together, leaving three 7-edge nodes in pink and a 3-edge node. The 3-edge node has three triangular neighborhoods. Two of those neighborhoods can be converted from triangular neighborhoods to signals at the lower level. The result will be that there will be one triangular neighborhood in green because it's the same as the whole ground state. This process of moving triangular neighborhoods down to become signals is called a pop down. This shows the triangular neighborhood where the pop down occurred. Now we have just the ground state that's completely flat. All of the distortion has gone away. This is the logical diagram for the outer approach of the collision of three defects to form a pop down. The three defects have to be configured in this fashion. When the defects are moved together, and at some point the defects eliminate themselves. We have this situation here where we have three triangular neighborhoods and three 7-edge nodes. When two of the triangular neighborhoods are converted into signals, well, then they disappear from this diagram and signals appear. And this is shown in this logical diagram here. So two of the triangular neighborhoods have disappeared and two signals occur at the signal level. The signals, of course, if you remember, at the next lower level of structure, the signals are toruses, either embedded in the pipes or as freestanding objects. Two triangular neighborhoods have been converted into two signals. These signals could be placed in a variety of different orientations, and it's not clear what exactly should happen. But this situation is not really as nice as I'd like it to be. I'll explain in the next section. At the conclusion of the pop-down, where two triangular neighborhoods are converted into two signals, the signals can be placed in a variety of different ways on the triangular neighborhood. The problem is that we'd like to have some symmetry for the causation of the pop-up, and so the most rational way of dealing with this would be to put three signals, and then that would trigger the pop-up, and the pop-up would look something like this, because only two of the three signals would be used. We'd have the now three triangular neighborhoods and one of the signals left there. This shows the triangular neighborhood in which the three signals are located. They will be converted from signals to triangular neighborhoods. This shows how 2 of the 3 signals in the ground state have been converted into triangular neighborhoods. So now we have 3 7-edge nodes and a new 3-edge node. So 3 edge rotations have been made, and the 3 defects are now in intimate contact with each other. 3 edges will be rotated. This edge here, this edge here, and this edge here, and this will have the effect of bringing the defects out. Now we've moved all 3 of the defects outward from here to here, from here to here, from here to here, and so now the defects are isolated. Each defect can continue in its own direction. This one going this way, this one going this way, and independently this one going this way. The conversion of signals into triangular neighborhoods is called a pop-up. The conversion of triangular neighborhoods into signals is called a pop-down. These 2 operators, I think, are very important. I've not yet had the opportunity to simulate the behavior of these events. I mean, they are programmed, and I know they work as explained. But the importance, I think, will come in the Big Bang video a little bit later. In an earlier video, where we started with a small tetrahedral triangle neighborhood network and grew it by the addition of 3-edge nodes, well, then the pop-up is the way that you can do that. And so my sense is that the pop-up and pop-down operators will play a very important role in the behavior of triangular neighborhood networks.